Hello students, welcome to Sapphirebluechemspark. Today let us start our session from inorganic chemistry, the chapter D and F block elements. So before enter into D and F block elements, we should know about the classification of long form of periodic table. So the long form of periodic table, actually it has four different blocks. One is S block, the other one P block, D block and then F block. So in this case, though we study about D block element, we should know how these groups are given to each block, because S block it has only maximum of 2 group, P block it has maximum of 6 group and D block 10 group and F block 14 group. How these numbers are limited? This is because of the maximum number of electrons that can be given to shells and the subshells are given by quantum numbers. So according to principal quantum number, the maximum number of electron for each shell is given by the formula 2n square, where n is said to be principal quantum number. So this principal quantum number is taken in this periodic table as n equal to 1 to 7. And each subshells, they have their own subshell. Then the subshells, they can have the maximum of 2 into 2l plus 1 electron, where n I said the principal quantum number, l is azimuthal quantum number, or we can say orbital quantum number. So the L that can have the values of L equal to 0, 1, 2, 3, and 0 represents the S subshell, 1 represents P subshell, 2 represents D subshell and the 3 represents F subshell. And according to substitute the values of SPDF in this formula, we can have S orbital can have 2 electron, P orbital can have 6 electron, D orbital can have 10 electron and F to have 14 electron. So based on this only, the maximum number of electron given to each subshell, the groups are given. S orbital 2. So this is first group, second group. How it is first group, second group? Each subshell, they have their orientation. So the orientations can have maximum of 2 electron. So yes, I said it can have only one orientation. The one orientation can have maximum of 2 electron. So S orbital, it has one orientation. That orientation can have 2 electron. One electron should be in upward, the other electron in downward. This is because of the spin quantum number, where the spinning of electron getting cancelled. And the next one, P orbital, I said it can have maximum of 6 electron. So P orbital has 3 orientation. Those are Px, Py, Pz. And these and all, this will be discussed in periodic classification as well as structure of atom. Now the D orbital, it has actually 10 electron in its subshell, maximum 10 electron. So here also D orbital, it has 5 orientation having 10 electron. Similarly, F orbital can have maximum of 14. So it has 7 orientations in those, each orientation having pairs of electron, that makes 14 electron. Okay, now how the groups are developed? This is because the valence electron or the differentiate electron or the last electron which is entering to which of the subshell that makes the element belongs to particular block. For example, if the S orbital electron, the valence electron enters to S orbital, then that element should come under S block only. Or if the electron enters to P orbital, that means P orbital, it has 1 to 6. So you can have, there are 6 group, 13 to 18. So in which first or orientation 1, second orientation, third orientation, fourth, fifth, sixth. So it can proceed like that only. So each element, they are having the last electron entering into their P orbital, getting filled up by 6 electrons in its given orientation. That's why why the p block is limited to only the 6 groups, and in which the p block it gets started after the filling up of s block. So we can have s block completely filled followed by p block. So we can write the s orbital filled followed by filling up of p orbital. Progressively it is filling to 1 to 6 electron. Similarly, when we go to d block, so in this case actually s orbital is being filled up, following that the d orbital it gets started. But the one thing, the first period, second period, third period, those and all, the first period it has only 1s, and the second period it has 2s, 2p, and the third period should have 3s, 3p, 3d. But the thing, according to Aufbau principle, because of the difference in energies of p d orbital and the 4s orbital, what happened? The electron preferably enters to the lowest energy level of 4s orbital, following that fill up with 3d orbital. So this is why after filling up of the 4s orbital only, the 3d orbital gets filled up. So in this fourth period, we can have 4s orbital filled electron, 3d orbital, following that 4p orbital. Similarly, when we go to that fifth period, what happened? The 5s orbital will be filled up. So I can have 5s filled up. After that, the 4d being filled up. Then 5p will be filled up. So successively we can write 6s orbital. When you go to 6s orbital, the element belong to third group lanthanum and actinium. They have 57 and 89 in its atomic number. After lanthanum 57, the next atomic number it starts 72. For rutherfordium it starts 104. So between of lanthanum to hafnium, 14 elements are there. Those 14 elements being filled in F block like F1 to 4. F1 to 14. How? This is why. The F block orbital actually when it starts the sixth period, the next electron, the next valence electron after the filling up of S block enters to F orbital only. So the F orbital once being completely filled with the 14 electron, then only it starts with the rest of the D block. So as the continuity number of 57 to 71 and 89 to 103, when you place in the same third period, then the 14 electron will shift the periodic table to the right extreme. So the entire group elements will be collapsed. So to avoid the collapsing, what we are doing, the electron when it enters into the F orbital, those are taken away from the D block and it is kept just below the periodic table, just to avoid the collapsing or the electronic arrangement of element. F orbital, F block elements are just kept below. But this is the part of the third group only. All these element, it is part of the third group. It starts third group and it extends over up to the 14th element, and in which the lanthanum and actinium are taken as the starting element of the one. The next one, after that, hafnium to mercury and rutherfordium to copernicium, they are placed over here. So when we go to the 6th period and 7th period, the electronic configuration gets reversed. How? It makes 6s orbital first of all, and then 4f orbital, after that 5d orbital, then it goes to 6p orbital. Similarly, for n equal to 7, the 7s orbital, 7th one, S block it being filled up, after that 5f is filled up, then 6d filled up, then it makes with 7p. So this is what the pattern of filling up of electrons in their orbital for each period. So up to third period we have 1s, 2s2p, 3s3p. But when we go to 4th period to 7th period, due to the difference in energies of s orbital with the d orbital and s orbital with the f orbital, the electron prefers to enter to the lowest energy level of s orbital, followed by the highest energy, the high energy. So this filling up of orbital, it is just given by Aufbau principle. According to Aufbau principle, electrons enter into the orbital which finds the lower energy. So the filling up of electrons in the orbital is according to their increasing energy. Okay. So this makes the periodic table into 4 different blocks: S block, P block, D block and F block. So this chapter we are going to discuss about D and F block elements. So the D block, it starts from the group number 4 to 7. It makes the d orbital being filled up with the valence electron. And the f orbital, it starts from 6 and 7. Though 4 to 7 d orbital are there, and we have the f block elements also along with the d block only. So those f block element kept away from the d block. So it is called inner transition element. But the d block is said to be transition element. Okay, let us start. How many D series are there and how many F series are there? Let us find the first transition series that starts from the period number 4. So the 4th period only the d orbital is being filled up with its valence electron. So this is said to be first transition series. So the first transition series in which the 3d orbital is being filled with 1 to 10 electron. So it starts from scandium to zinc. This is called first transition series, or it is said to be 3d series. The next second series, it just belong to 5th period, where the 4d orbital is being filled with 1 to 10 electron, and it starts from the element yttrium to cadmium, and it is said to be second transition series. The third transition series, it belongs to period number 6, where the 5d orbital is being filled with 1 to 10 electrons. So it is said to be 5d series, that has the element starts from lanthanum and hafnium to mercury. Then the last period, 7th period, it has the 4th transition series, or it is said to be 6d series, where the element actinium and then it has the next member Rutherfordium to copernicium. So these are said to be, we are saying, the D block element. So lanthanum, continuously we are not supposed to write. After lanthanum, the element it starts with hafnium. Similarly, after actinium, the element starts with Rutherfordium. So these are said to be the D block element. So D block, it has 4 series: 3D, 4D, 5D, 6D, or we can say first transition series, second transition series, third transition series and fourth transition series. From this third and fourth transition series only, we have taken away the F block element, where the valence electron enters into the F orbital. So in this case, first of all, the 4f orbital is being filled 1 to 14, and then the series belongs to 7th period, where 5f is being filled with 1 to 14 electron. So this is said to be F block, and it is called 4f series is called lanthanoid series and 5f series is called actinoid series. When we say about the electronic configuration of D block, you may find the electronic configuration, it becomes ns to n minus 1 d 1 to 10. This is why the n is equal to 4 to 7, but the n minus 1 is equal to 3 to 6 only, because we have to subtract 1. This is why, because we said when we go to 4th period only, the 3d orbital is being filled up. So this n minus 1 orbital is said to be penultimate orbital and nth orbital is said to be ultimate orbital. As well as in the F block, we have ns orbital fully filled and then n minus 2 f orbital being filled, following that n minus 1 d orbital. So the F block, it has ultimate orbital, penultimate orbital as well as anti-penultimate orbital. So this is called ns orbital is ultimate, n minus 1 is said to be penultimate and this n minus 2 is said to be anti-penultimate. So how we can say the valence electron, if at all goes to the penultimate orbital, then it belongs to D block. Or if the differentiate electron enters to anti-penultimate orbital, then it makes F block. So correspondingly, we can have the different electronic configuration for each series. Electronic configuration of first transition series 4s to 3d 1 to 10. So we can write 4s to 3d 1 to 10. Similarly, this is 5s to 4d 1 to 10. Then next one 6s to 5d 1 to 10 and then 7s to 6d 1 to 10. These are the outermost electronic configuration. These are the electronic configuration of each period. But this is the electronic configuration of D block element as it is taken as the general outer electronic configuration of D block element. Okay. What are called transition element and where it is positioned in the long form of periodic table? The D block is kept just in between of S block and the P block. So the properties of S block element gets transitioned over D block and it goes to P block. So we know well the left extreme of the periodic table they have metals and right extreme of the periodic table they are non-metals. So here the non-metallic property and non-metallic property varies, not only their property, even all the periodic properties are varies from S block to P block. So all these properties are getting transitioned in the D block only. For example, we have most metal to most non-metal. So in this the left extreme, when we say it is highly metal and these D block elements where the metallic property slowly decreases and it approaches to non-metallic property when we enter into the P block. So such a way the properties of these elements transitioned from S block onto the P block. That's why the D block elements are called as transition element. And from this transition element is the F block is kept away. So this is called inner transition elements. Position of D block elements we discussed. The position of D block element is just in between of S and P block in the long form of periodic table and hence they are also said to be transition element. So these transition elements that include the group number from 3 to 12. So 3 to 12 we have actually 10 groups. So each period they have 10 groups in its series. So in this the first transition series or even every transition series they have 10 elements. Totally it makes 40 elements in their group. So how these transition elements defined? The transition elements are the one. They should have only the partially filled d orbital from 1 to 9 either in its ground state or in its simple ionic form. Those elements only called transition element. So the 12th group that contains the element zinc, cadmium, mercury and copernicium are not truly transition element. This is why because they have fully filled d orbital in its elemental state as well as in its ionic form and hence the 12th group elements are not regarded as transition element. Both of the questions are highly important. So the elements zinc, cadmium, mercury and copernicium, they belong to 12th group, in which the d orbital is fully filled in its elemental state as well as in its ionic state, and hence they are not regarded as transition element. General outer electronic configuration of d block element is n-1, d1 to 10, ns1 to 2. So the ns orbital, they can have either 1 electron or 2 electron in its orbital. The d orbital, it has 1 to 10. That means the d orbital is progressively filled by 1 electron to 10 electron when we move from each element from 3rd group to 12th group. And if we find the electronic configuration of individual series from 4th period to 7th period, we have 4 transition series, and in this we can have 3D series, 4D series, 5D series, 6D series. 3D series where the 3D orbital is the valence shell of the series, so in which only the electron enters into that, so we are getting 3D 1 to 10, 4s 1 to 2. And in 4D series, they can have 1 to 10 in 4D orbital followed by 5s 1 to 2. For 5D series, it is 5D 1 to 10, 6s 1 to 2, and 6D series 6D 1 to 10, 7s 1 to 2. So the differentiate electron that enters into penultimate orbital after filling up of the ultimate orbital. Penultimate orbital, anti-penultimate, ultimate. Just for example, let us consider nth shell. Nth shell, we said it has 4 subshell S, P, D and F. If I consider only the nth shell, what I can do? The energies of these orbitals are S orbital is lesser energy than P orbital, which is less than D and F. So in this, the electron being entered into that is the increasing order of energies. So first of all, S orbital filled up followed by P orbital, and in between of this the D and F orbital enter because the energy of D and F orbital are lower than their 4s or 5s or 6s or 7s orbital. So in this case, suppose if I draw the subshell of nth shell, I may say this is the nucleus. Just imagine this is the nucleus and it has some core electron. So I can say this is said to be a core. Core means before nth shell we have K shell, L shell, M shell. Those electrons are being present along with the nucleus. So this makes the core. Now let us represent nth shell. Nth shell, actually the last shell is S orbital. For example, if I consider 7th shell. So 7th shell, S orbital is 7, P orbital 7, but D orbital 6 and F orbital it becomes 5. So how I can designate? The F orbital becomes the 1 followed by the D orbital, after that only the S orbital. So this, if I say it is 7s, this will be 6D and this will be 5F. So you can say the D orbital just in the last orbital, the outermost orbital of this is S orbital and it is said to be ultimate. And just before S orbital, I have D orbital. So it is said to be penultimate. And one more orbital I have, it is just before the D orbital, that is said to be anti-penultimate orbital. So after filling up of S orbital only, whether the valence electron that may enter to D orbital or to the F orbital. So this is what we are saying, yes, ultimate orbital, penultimate orbital and anti-penultimate orbital. So such a way, when we discuss about the transition series and their electronic configuration, it is said to be 3D10, 4D10, 5D or 6D. So here the D orbital that makes a penultimate orbital and S orbital that makes ultimate orbital of the given element. In this series, here sum of the element. For example, the elements belongs to group number 6 and group number 11. They have their electronic configuration in different manner. Actually, we used to write the electronic configuration, for example, chromium and copper. Chromium atomic number 24, so it's inert gas configuration argon followed by the 4 electron present in d orbital and 2 more electron in s orbital. So we can say argon 18 and 4 22, 22 plus 2 24. And in copper it is 29, so where this makes 18, 18 plus 2 20, 20 plus 9 29. This is what actually we are expecting for copper and chromium, but in this case as it has the d orbital partially filled with 4 electrons, so it has only 1, 2, 3, 4 and one more orbital being vacant, but the 4s orbital is fully filled with 2 electrons. So in this case the exchange of electron can be allowed because the difference in energies of the orbital is very little. Therefore the 4s orbital electron that can shift over to d orbital. So its actual electronic configuration that comes 3d5 4s1. Similarly for copper it has 9 electron and the 4th. So one of the s orbital electron can enter into the d orbital, so that makes a 3d10 4s1. So the actual electronic configuration of chromium and copper, argon 3d5 4s1 and copper argon 3d10 4s1. This is why, because according to the Hund's rule of maximum multiplicity, the half-filled orbital and completely filled orbitals are more stable than we expected, and hence the chromium, copper, they are getting their actual electronic configuration such a way. General properties of transition elements. So hereafter we are going to discuss about all the general characteristic properties of transition element. So first property, metallic character. We said the d block elements are metals, but actually the metallic nature of these elements are lower than that of s block element. S block only the strong electropositive as well as most metallic in nature. So actually these metals, they possess a characteristic crystal lattices that might be of HCP, hexagonal closed packing, CCP, cubic closed packing, or body centered closed packing. So either of these simple cubic lattices they possess by these elements. But zinc, cadmium, mercury and copernicium, they do not have such typical crystal lattices. And here one or more element, they can have more than one form of crystal lattices also according to their combination. Then being they are metal, they exhibits all the metallic properties like lustrous, malleability, ductility, conductivity, high density, etc. So lustrous, it defines about the shining nature. Malleability, that can be beaten into thin sheets. Ductility, that can be drawn into thin wire. And conductivity, it can conduct both heat as well as electricity. And in this case, the electropositive character of this metal goes on decreasing when we move from left to right because of the increasing effective nuclear charge. So when we discuss about the electropositive character of transition element, it shows the gradual decrease from left to right. This is why, because whenever the valence electron enters into the d orbital, there would be increase in one proton in its nucleus also. So as the valence electron increases, the protonic charges also increases, and hence the effective nuclear charge increases. When effective nuclear charge increases, increases, there would be a total reduction in the size of the atom. So the positive character, metallic character also decreases across the period. And these metals, they have very high atomization enthalpy as well as very high density. This is the reason why, because the metals, they possess a strong metallic bonding among them. So if we plot the atomic number versus enthalpy of atomization, we may find the middle series element, they possess very high atomization enthalpy compared to the lower end or the lower right end or even the lower left end of the elements. So due to the presence of increasing number of d orbital electron, they become hard and possess high density as well as enthalpy of atomization. When we talk about the filling up of d orbital, what happens? Every electron that enters into the d orbital just 1 by 1 only. So when I move from scandium to manganese, the electron that enters such a way. So we can find the number of unpaired electron goes on increasing from scandium to manganese. But when we move from iron to zinc, what happens? The pairing of electron takes place. So for iron it becomes 26 and cobalt 27, nickel 28, copper 29, zinc 30. So in this case you may find the number of unpaired electron first of all increases from scandium to manganese, and then number of unpaired electron decreases from iron to zinc. This makes the metallic bonding among themselves. When they possess a large number of unpaired electron, they do have very high atomization enthalpy. When pairing of electron takes place, atomization enthalpy decreases. This is the reason we can have the middle series of the elements. They possess very high atomization enthalpy due to large number of unpaired electron in it. So number of unpaired electron increases, atomization enthalpy also increases. When number of unpaired electron decreases, atomization enthalpy also decreases. The next property of transition metals, melting and boiling points. As we said, d block elements are metals, so they do possess a high melting point as well as boiling point. This is because of that the metals, they do have their strong interatomic interaction. Interatomic means the bond distance between the atoms is very less, and it is somewhat in nanometer distance, and hence they do find a strong interatomic interactions among their metallic atoms. That's why they have very high melting and boiling point. But actually the melting and boiling points are in connection with the number of unpaired electron present in the d orbital. So when we have the electronic configuration of d block element, we said we have n-1 d 1 to 10 and ns 1 to 2. So in this case the valence shell, it includes both d orbital as well as the s orbital. So here the d orbital having the maximum of unpaired electron up to the middle series, and after that the d orbital being paired up. So we may find in the graph, when we plot against atomic number versus melting point, that manganese and the technetium, they do show anomalous property against the melting point. This is because this manganese and technetium, they have 3d5 4s2 orbital and technetium 4d5 5s2 orbital. So in this case the d orbital itself half filled along with the fully filled s orbital. So that makes exceptionally stable for manganese and technetium. So this may cause a reason for the dip of melting point of manganese and technetium. But all other elements, chromium, molybdenum, tungsten, they have very high melting point when we compare with all other elements. In this case, all of them, they have d5 orbital and s1 orbital. So, d5 is half-filled as well as s orbital is also half-filled. So, the total number of the odd electron is maximum for the elements of chromium, molybdenum and tungsten, and hence the strong interatomic attractions will also be greater. So, number of unpaired electron, if at all maximum, then their melting point that shows the higher value towards the middle of the series. Once the number of unpaired electron decreases, where the melting point of the series also decreases. Okay students, let us close our today's session. Today we discussed about what are the d block elements and what about its position in the long form of periodic table and few of their general characteristics. Let us continue the same chapter the next session. Until then, bye bye.